All right, welcome to our Yebo Tutor session. And in this session, the whole idea is we are working out chemical bonding. The topic lies under molecular structure. So if you still remember last time, we said we're focusing on molecular structure. So it obviously starts from chemical bonds, the molecular shapes, electronegativity. Let me just do this, and then bond polarity, bond energy, bond length. Then we also have intermolecular forces. So these also use the chemical bonds concepts. So types of intermolecular forces, states of matter, density, kinetic energy, temperature, and so forth. And then we will focus on ideal gas theory next week. Maybe the next 2 weeks, right? We can focus on ideal gas theory for the next 2 weeks. So the questions that we have are from papers. Let's take our papers, and also we will obviously use our data sheet. So remember, we said we have a data sheet. So if you use this data sheet from the exam paper itself, you get used to it, so that when the day of the exam comes, you are not frightened. It's just one of the things that you're used to working with. Okay, so let's get right onto it. So the first question will come from the 2018 paper, and what I've just done is to just select the questions so that we focus on questions that are relevant to the topic. The instructions are there as usual, and then you've got these multiple choice questions. Right, so our first question reads as follows, 1.1. The tendency of an atom to attract the bonding pair of electrons is known as what? The tendency of an atom to attract a bonding pair of electrons. What is that? The tendency of an atom to attract the bonding pair of electrons. So when we're creating a chemical bond, there's always a property that dictates that bonding process. So let me just go on to, for example, our data sheet, right? There is a property in this periodic table. There's a property in this periodic table, and that property deals with what we're trying to calculate right now. It deals with how electrons interact. So there's a tendency of an atom to attract, right? The tendency of an atom to attract the bonding pair of electrons. The tendency of an atom to attract the bonding pair of electrons. So there are certain properties that are here that make certain atoms attract the bonding pair of electrons as compared to others. So the options that we have, this is our first question. I will call this question 1 for the 2018 paper. So let's just say paper 2018, question 1. Okay. The tendency of an atom to attract the bonding pair of electrons. So we have electron affinity, electronegativity, polarity, activation, energy. So this is attracting, this has to do with attracting a bonding pair of electrons. Attracting a bonding pair of electrons. So we have electron affinity. What is electron affinity? There are some options there. We need to choose the appropriate or the correct option. What is electron affinity? What is electron affinity? And what does it have to do with attracting electrons? Remember, this is a tendency, isn't it? This is a tendency. So this is a tendency of an atom to attract the bonding pair of electrons. And this is a tendency of attracting a bonding pair, not just attracting electrons, attracting a bonding pair of electrons. So the question is which option there is true? Which option there is true? Attracting a bonding pair of electrons. Which option there is true or makes sense? So we have electronegativity as the second option, polarity as the other option, activation energy is the last. Right. So I think if you look at this question, you will discover that the keywords that we are discussing are attracting electrons, right? We are attracting electrons, right? We are attracting electrons. But the electrons that we are attracting are for bonding. We are attracting electrons, but the electrons of interest, the electrons that we are discussing about are not just electrons. These are bonding electrons. So the criteria that you use to come up with this tendency must be based on chemical bonding. Must be based on chemical bonding. So in your understanding of chemical bonding, what would be the property? This tendency. Is it electron affinity? Is it electronegativity? Is it polarity? Is it activation energy? In other words, define each and every one of the terms. Define each term and come up with your suggested reasoning, the correct answer. Right, so I think by now you've gone through your notes and you've done some reading. So this one is a matter of just reading so that you can capture the correct response to it. So our obvious selection there would be your electronegativity. Your obvious selection there would be your electronegativity. Why electronegativity? Just because with electronegativity, all you are looking for are bonding electrons. And the bonding electrons are pulled closer by the more electronegative atom, right? The more electronegative atom will pull the bonding electrons closer. So this is what is taking place in this question. Any questions based on that? Any questions based on what has been discussed here? Are there any questions based on this discussion? So just get the definitions. Get the definitions of electron affinity, get the definitions of all the terms, and then choose that. Excuse me, the most appropriate is our electronegativity. All right, let's just see if we have something, if we have a tool that can show us our bonding structure, right? So this tool, I want us to probably use real molecules. I'm not sure if you can see here. I'm mostly interested in the actual arrangement of the electrons, right? Actual arrangement of the electrons. Right. I cannot see some, okay, electron geometry. Let me just see. Okay, so this is electron geometry. I'm looking for some electrons. I'm looking for some electrons. Some bonding structure with electrons. So we can build a molecule, I guess. Let's see if we can build a molecule there. The whole idea is if we can see it, this is molecule polarity, right? Molecule polarity could be, it could be useful. Let's see if it can work. Let's see if it can work. Right, if you are joining us just now, we are attempting questions from 4 papers. So we'll jump onto each paper, hopefully to finish all the questions. So we have molecule polarity and we want to build molecule polarity here. Okay, so we can't run it on this, right? These are partial charges. These are partial charges, and then we take it from there. Right, these are partial charges, then we take it from there. Right, so we've got electronegativity. There's some electronegativity as an option here. Atom A is this yellow atom. Atom B is the center atom. Atom C is that atom. So just out of interest, okay, this is just showing us, okay, something else. I'm not interested in that. But what I want us to see is if we have a more electronegative atom, what happens to the electrons. So there is something that we can maybe make use of here, which is the partial charges, right? Yes, the partial charges. The partial charges can show us the atom that collects, or the atom that ends up having more. But the other problem with that is that you can have bonding electrons and not have an indication of the partial charges from that. Right, but let's just see if we can see something here. Atom B, if we make it more electronegative, right, we're getting okay, so this is not going to give us, this is just getting an ionic bond, but it's not going to give us what we're looking for. It's not going to give us what we're looking for. So let me just see if that other tool can load, and then we can see if we observe that electronegativity. If we have our electronegativity, we can pick it from the periodic table. Right? So there's a list of elements there with their different electronegativities. All we want is to at least compare. And this tool we can't compare because they have oxygen and hydrogen at the moment only. Okay. All right. So maybe for now it's a matter of just reading. It's a matter of just reading so that you can familiarize with these terms. So there we go. Electronegativity. The next question for the 2018 paper on this topic, the next question has to do with bond length. So bond length is the average distance between what? Bond length is the average distance between what? A, orbitals of two bonded atoms. B, electrons in two bonded atoms. C, nuclei of two bonded atoms. And then D, molecules of the same substance. Right. So bond length is the distance between what? Bond length is the distance between what? Let's hear out your answers. It is the distance between what? Do we have, if we want to build a molecule, can we see bond length? I do not see an option that can give us a bond length on this tool. Let's see on that tool. We get an electron density, we get a bond dipole, so they show us the atom that is collecting more electrons, isn't it? So we've got the more negative atom. The higher the electronegativity, the higher this polarity. Okay, so let's just see. Partial charges are available. Those are the partial charges. Bond character is just shown there. Either it's covalent or it's ionic. So we wanted to see the length, isn't it? The bond length, and we can't see it there. Here we obviously can't see the bond length. Let's just see. Put it with that. We won't be able to see the bond length. So we are just trying to find. Okay, we're trying to find some characteristics of the bond, right? Characteristics of the bond. right? Characteristics of the bond, right? So I'm not going to be able to pick it here again because we can't see where the bond starts, right? You can see where the bond starts, right? So we have some objects here. These are just bond angles, so it's not going to help. Right here is for us to build an atom, and this is the molecule geometry, just bond angles, and we cannot tell any more information from that. Okay, so I can't show you a measurement that has to do with the bond length, but otherwise theoretically you still remember that the bond length is the average distance between the nuclei of the two bonded atoms. So it's as if you're measuring it from the center. So that would be now question number 2. So for our bond length, we're just looking at, this would be, let's call it nuclei of atom 1. So that is atom 1 and then atom 2. So obviously the nuclei are exactly in the center. I'll try to approximate that. And then our bond length is measured from this nuclei to the nuclei. That becomes our bond length. Okay, so our selection for this one would be between the nuclei of the bonded atoms, So that would be nucleuses, right? Nuclei would stand for nucleuses. If we could use that word, it's just a plural for nucleus. So 1 nucleus, 2 nuclei, 3 nuclei, and so forth. So the distance between the nuclei is now our bond length. The distance between the nuclei is now our bond length. Any questions on that part? You can just put them in the chat, or you can send them so that we can discuss the questions. Right, the next available option for us to attempt has to do with question number 1.3, and this question is asking us to discuss hydrogen bonds and London forces, which are also called induced dipole forces. They have a common characteristic in that. Option number 1 is, option A is, they are both stronger than chemical bonds. So there's some keywords that are already saying here. They are saying they're both stronger than chemical bonds. So this is what we are. Remember, there are 2 types. We've got our chemical bonds, which are atom to atom bonds, and then we have intermolecular bonds. Right? So second option, both occur between non-polar molecules. They both occur between non-polar, which means for you to pick the right answer for this one, you need to remember the types of molecules that form hydrogen bonds within, let's say, among or between, and then the type of molecules that form London forces or induced dipole forces among between adjacent or nearest neighbor molecules. Then C, both occur between polar molecules. These both occur between polar molecules. Now, you will now have to think about polar molecules. When you have polar molecules, is it possible that we have hydrogen bonds? Is it possible that we have London forces, which are induced forces? Then the last one would be they are both intermolecular forces. That's the last option, right? So which option are you going to pick from this? Which option are you going to pick from this? Hydrogen bonds. What are hydrogen bonds? So hydrogen bonds, that's question 3. Hydrogen bonds are formed. Hydrogen bonds are formed When we have a highly electronegative atom, so you have a highly electronegative atom, electronegative atom, usually your nitrogen, your oxygen, and so forth, bonding with hydrogen, right? So that is your starting point. You have defined these, right? The hydrogen bonds. Next, London forces. London forces. The London forces now. How do you define London forces or induced dipole forces? London forces or induced dipole forces. Induced dipole, you have, these are now intermolecular forces, right? So these are bonding. Let's say these are bonds between, this is what? This is induced dipole. If you have, okay, so let's maybe just list, the types of what, of participants, right? And the particular bonds that can be formed between the participants. So obviously we have ions, right? Somewhere there. So we just want to maybe categorize our types of bonds so that we can identify these London or induced dipole bonds, induced dipole forces. Right, so we've got some ions. Ions can bond with ions, isn't it? Ions can bond with polar molecules or the weakly polar so weakly polar molecules. Ions can bond with polar molecules or weakly polar molecules. We can also have maybe let's color these so that we won't forget, right? So the ions will be in green, will be in red. Then our polar molecules will be in purple. And then our weakly polar molecules, let's see if we can put them in black, at least colors that would stand out. So if we have on the right hand side, so let's just have both on the left and on the right hand side, right? Let's just have both on the left and on the right hand side. So let's copy that and then let's paste that. So this is our arrangement. For the sake of space, let me maybe actually do this so that we don't crowd. So what I want to try to do here is to tabulate. We want to tabulate what we have here in such a way that we can easily identify the type of bonds that will be made. So that's what we want to do here, so that we can easily identify the type of bonds. Right, first of all, I hope you remember. That the criteria that you use for the type of bond selection or the nature of these molecules, whether we say the molecule, we're talking of ions, we're talking of polar molecules, or we're talking of weakly polar molecules. I hope you remember that electronegativity is the criteria. The difference in electronegativity is what determines if we will end up having ionic bonding, end up having polar or types of bonding between polar molecules and that. Right. So you actually create the molecule first by looking at interatomic forces, right? Then after that you look at the you use the electronegativity to determine the polarity of your molecule. Okay, so if ions bond, if there is a bond between an ion and an ion, so let me just say ion, This is a polar molecule. Polar molecule. Another polar molecule. Weakly polar molecule. Weakly polar molecule. Okay. So if we have ion to ion bonds, right? So you can have, for example, sodium and a chloride. So ion to ion bonds would form an ionic bond, isn't it? An ionic bond. How about if an ion, attempts or is reacting with a polar molecule? What kind of a chemical bond formed? If an ion is combined with a polar molecule, what kind of an ion is formed? What kind of an ion is formed? What kind of a, let's say, what kind of a bond is formed by this ion interacting with the polar molecule? What kind of a bond is created by this ion that is interacting with this polar molecule? What kind of a bond between this ion and this polar molecule? Ionic bonds, we're happy. How about an ion with a polar molecule? So if the ion bonds with a polar molecule, so let's put it like this. Let's put it like this. Let's just do it this way. Right. So the type of bond that would be formed between an ion and a polar molecule is now a what? The type of forces that are experienced there. These are, what are these? The type of forces that are experienced between an ion and a polar molecule. That is what? An ion dipole set of forces. Ion dipole set of forces. Because the polar molecule will usually has a polarity, a delta charge there, a delta charge there. This one, the ion, is strongly charged, right? Or it's strongly charged. So you've got this ion dipole this ion dipole bond. Let's also put some dipoles here. Okay, so our next is if this ion interacts with a non-polar or a very weak, a non-polar or a very weakly polar, with a non-polar or a very weakly polar molecule, what would happen? The weakly polar molecule does not easily polarize, or it cannot easily self-polarize. So this ion is what is creating, right? This ion is what is creating it's now creating the bond, isn't it? So this ion is now what is forming the bond, and the bond between those weakly polar, right? Weakly polar and this ion. The ion is now forming that bond, and that bond is obviously now ion-induced dipole. It induces a dipole in this molecule. So in this second case, we have ion-induced dipole forces. Ion-induced dipole forces. Ion-induced dipole forces. Okay, the ion is the agent that generates, or it sets up polarity in this molecule, which is otherwise not polarized. Right, so we have listed ionic bonds ion dipole forces, ion-induced dipole forces. Let's go on to the other side. Let's go on to the other side. Let's start with this polar molecule. Let's start with this polar molecule. The polar molecule, its interaction with the ion, we already have it. Where? We already have it here. We said between the polar molecule and the ion, you would have an ion dipole forces. How about a polar molecule and another polar molecule? How about a polar molecule and another polar molecule? So this is now what you're trying to do here. We want this polar molecule to interact with another polar molecule. We want this polar molecule to interact with another polar molecule. So I'll try to now put it like this. This is the interaction that we now have. Polar molecule interacting with another polar molecule. So what do we have? We have a dipole, partial charges. The more, if there are no lone pairs, right, you will find that there is another atom that tends to pull all these bonding electrons. Even oxygen, sorry, even water. In water, I think we should be able to see water in one of our tools here. So let's just look at water. In case you are joining us, let's just see if there's someone who has joined us. In case you're joining us, please feel free to interact with us and to post your questions either this or the chat group. Right, so what am I looking for? I'm looking for a polar molecule. Looking for a polar molecule. Our molecules that are known, I think I picked one here, isn't it? H2O. So we've got a lot of molecules here, right? We've got a lot of molecules here. Very interesting shapes, right? Very interesting shapes. So let's look at water. So this is our polar molecule and it's water. Now, what's taking place with our water molecule? What's taking place with our water molecule is that if we were to have one water molecule, it has an oxygen that is bonded. So in our case, the oxygen is this orange species that's in the center there, right? This oxygen is bonded to two hydrogens. This oxygen is bonded to two hydrogens. So we have an oxygen, we've got a hydrogen and another hydrogen. Then what are these things that you're seeing on top there? What are these things? It's a pair of these things and another pair of those things. So these two pairs are two lone pairs. Two lone pairs. So that we have how many electrons in the shell? I guess you can figure that out. So if we have these two lone pairs and we have two bonds, right? If we have these two lone pairs and we have these two bonds, because oxygen is the more electronegative, so it is highly electronegative. So oxygen, highly electronegative. Negative. If it is highly electronegative, do you notice, right? Do you notice that if it is highly electronegative, in our case, what is taking place is that oxygen is pulling all the bonding electrons to it. It pulls all the bonding electrons to it in such a way that on this chemical bond, the electrons are closer to the oxygen. Remember, these are two electrons that are bonding, isn't it? There is a bond that is being created by these two electrons. One of the electrons belongs to the hydrogen atom, the other belongs to the oxygen. But now the problem is the oxygen is collecting all the electrons, right? In this other bond, right? In this other bond, since I'm now on Lewis, since I'm now using a Lewis structure, let me just remove that and also remove that. Oxygen is, on the other side, we also have this oxygen had its own outermost electron. Then you have what? Then you have hydrogen. So for you to get perspective on those numbers, you can actually just come to your periodic table and you can see that oxygen is in group 6, isn't it? It's in group 6. In its outermost shell, we have 6 electrons available, right? In its outermost shell, we have 6 electrons available. So if we have 6 electrons available in its outermost shell, then these are the 6 that are participating in the bonding. These are the 6 that are participating in the bonding. 2, 4, 6. The hydrogens, 1 electron. Right, so now that we have this arrangement, oxygen has collected all the electrons. So when it takes an electron from the hydrogen, what is the net charge that this hydrogen atom remains with? If we remove an electron is negatively charged. What is the net charge? This hydrogen will remain with a net charge. We're just putting a delta. It is representing a tiny value of electronic charge. So we have that net charge for this hydrogen, that net charge for the other hydrogen. Then what happens in the net charge of this oxygen? This oxygen becomes negatively charged. So you've got a molecule which has 2 poles, right? You've got a molecule which has 2 poles. So because of that, you will see that in its shape, we see this situation here. We see this situation here where our hydrogens, the moment you just move the hydrogens, the electrons are trying to be as separate and as stable as possible. So we always have this arrangement. So we now have a measure, right? We can also see this on this molecule polarity example. Right? We can also see this on this molecule polarity example where we have 3 atoms as an example. So if we have 3 atoms, we want a hydrogen here, isn't it? We want a hydrogen here. Let's just maybe see if we can go on to build a molecule. Right? Build a molecule. I hope we have hydrogen somewhere. Yes, we do. Good. So this can be a very good exercise for us to build this molecule because it will work for us in this case. So this is our oxygen atom. So oxygen atom, happy days. Let's now take 2 hydrogens, right? So we bond that oxygen with that hydrogen, then we bond that oxygen with that hydrogen. So this becomes our molecule. That becomes our molecule. So the lone pair of electrons repel each other. The lone pair of electrons repel each other, hence the arrangement here. And then we have our hydrogens also arranged in that way. So what we are just seeing is a model that is showing our oxygen in the center, our hydrogens in the other sides, right? Our hydrogens in the other sides. So basically that's our water molecule. So the polarity is what we're just discussing here. We can experience that. Let me see if I can refill. Can I refill? I don't think I can refill. Okay, I cannot. Okay, I just wanted to try something. Okay, so we now have these molecules. Let me just clean this out so that in the end we have polar. So if we have 2 water molecules, remember the arrangement of the dipole, right? Remember the arrangement of the dipole. So if we have 2 water molecules, the oxygen is more negative, the hydrogens are positive. So it's obvious that these hydrogens, if we have 2 water molecules, these hydrogens will interact with the other oxygen of the other molecule. So I cannot, let me just see if I can, okay, I cannot do that. All right, fine. Let's just see if we can work through what we have in the same way. What I'll do now is just look at the electronegativity. Let's compare electronegativity. Let's go to our table. So we have hydrogen, it has an electronegativity of 2.1. Then we have oxygen, very high electronegativity. So I want to just model this so that we can see it. Hydrogen, let atom A be hydrogen, let atom C be also a hydrogen. So let's put less electronegativity on atom A, right? That would be 2.4. Sorry, 2. Maybe let's put it here. What is the scale? This is just less or more. So let's say less is a 0, which never really happens. Let's just maybe say it's a 0, and then let's put a 1 here. Let's put a 2 there. So oxygen would be very highly electronegative, and then our atom A and C, which is, this will be atom C and atom A. So that is what would happen, right? All the electrons, can you see, all the electrons are being pulled to atom B. All the electrons are being pulled to atom B. And in the end, we have atom C and atom A being positively charged at peace. And the center is now negatively and very strongly negatively charged. It means if you put a second molecule which looks exactly the same, then these molecules would interconnect. So maybe there's another tool. There's another tool that I think we used last week. I think it's the states of matter tool. Let me just see if it is the one. And we might also need this. Moment. Might also need this. Might also need this. I think atomic interactions, right? Right, there's an atomic interactions. There we go. Right. I think this one could actually be helpful for your bond. That question on bonds. Right, so atomic interactions is coming up, but the state of matter 1 had the water molecule. So I just want you to observe the way the water molecules are arranged, right? Observe the way the water molecules are arranged. This can actually give you some, this is good. This is good. So this is our atomic interactions program to help us understand atomic interactions. So I think we should be able to see, that question on what? On bond length, right? That question on bond length. You can actually see what happens there and the distance that we're measuring. So this is the distance between atoms, and this is our scale. So this is our reference. What do you call it? Atom, and this is the other atom that is moving away from the initial, the first atom. So okay, we'll use this. Happy that we can at least simulate. Right. So let's look at state of matter. It has water. So I want water. Right. Look at that. This is our water molecule simulation. We used it last time. So on the water molecule, by the way, water is a polar molecule, right? So we have a polar molecule called water and another polar molecule called water, and they're interacting, and obviously these are within the same container, like we see. So can you see this? Let me just remove all these other things. So can you see that the red is representing the oxygen, isn't it? Because it's the center atom, and the hydrogens are like its ears. Do you see something here? Every point where we have the hydrogen, which is in white, the interaction that that hydrogen has with the next molecule is with the red molecule. Can you see that? Each hydrogen, which is white, is interacting with an oxygen, which is red. The white hydrogen of the other molecule will interact with the oxygen, which is the red molecule of the red atom of the other molecule. So that's this dipole forces. So we are just discussing here dipole forces, because it's two molecules that have what? That have a dipole set of arrangement. So we have dipole forces that can be experienced here. So we have seen for the polar molecule, right? For the ion, we have seen its interaction with another ion. We've seen its interaction with a polar molecule. We've seen its interaction with a weakly polar or non-polarized non-polar molecule. The polar, we already know its interaction with the ion, which is the ion dipole. Then we've seen the interaction of the polar molecule with another polar molecule. Then the next would be what would happen in between a polar molecule and a weakly polar molecule. So let's draw it here. A polar molecule and a weakly polar molecule, or a non-polar molecule. A polar molecule and a weakly polar molecule. What is the interaction? What is the interaction? Please pick it up. Please pick it up. What is the interaction between a polar molecule and a weakly polar molecule? Polar molecule and a weakly polar molecule. So this polar molecule has a dipole, isn't it? This weakly polar molecule, it usually polarizes when there is something that is charged that approaches it. So in this case, a dipole approaches it. A dipolar molecule. So you've got a dipole that induces a what? A dipole. Because in these molecules, you can only have induced dipole. So that will be your dipole-induced dipole forces. Your dipole-induced dipole forces between the polar molecule and the polar molecule and the non-polar molecule. Right, now we're happy. We have an interaction of the polar molecule with all three. With the ion, we've seen it, right, when we started. With another polar molecule, we've seen it, and with the weakly polar molecule, we have seen it. So we are done with this one. How about the weakly polar molecule? The weakly polar molecule, we've already seen its interaction with the ion when we were looking at the ion to start with. Then the weakly polar molecule, we've seen its interaction with the polar molecule. So the next question is, what is the interaction? What are the forces that are set up when a weakly polar molecule interacts with another weakly polar? These are intermolecular forces. These are intermolecular forces, right? But I'm just seeing some messages there. They're not defined as to what Artem, Ons, and John are saying. So please, when you want to comment, you can just state exactly what you would like to contribute, ask, or otherwise. So when we have a weakly polar molecule and another weakly polar molecule, can we have intermolecular forces? Can we have intermolecular forces? We find that these materials which have molecules that are weakly polar or non-polar, they will actually interact. You can actually freeze them, right? So that's intermolecular forces. So this would be very weak intermolecular forces. And the question is, what is the name of these? This is an induced, usually it works with an induced dipole. So you would only have your induced dipole forces. So this would be induced dipole forces. They induced each other. This one induces the other one, and that one, now that it becomes polarized, it induces another. So it is okay, the process, you can read about it maybe in another text, but otherwise in basic interactions, these are the types. So our question should be easier now. Right? Our question should be straightforward now. So it said hydrogen bonds. We already have seen that, for example, we do have hydrogen bonds with our water, and then London forces, induced dipole forces, and we said these are the so what they have in common? Are they stronger than chemical bonds? No way. These are intermolecular forces. So chemical bonds, we actually have interatomic. So the next one, both occur between non-polar molecules. They both occur between non-polar molecules. The London forces do occur between non-polar molecules, but the hydrogen bonds, right? The hydrogen bonds would occur between, can occur between polarized polar molecules. So B is not going to work because it says both. It says both. So it's not going to work for hydrogen bonds. Then both occur between polar molecules. Both occur between polar molecules. Hydrogen bonds, yes. London forces, no. Isn't it? London forces, no. So C is not going to work. And then they are both intermolecular forces. They are both intermolecular forces. The last one is correct because yes, we have intermolecular hydrogen bonds. So we already picked, we said between hydrogen and any strongly electronegative atom. So we said, for example, water, isn't it? Some water there. So it's obvious that it's an intermolecular force, right? It's an intermolecular force. Then we also have the London forces, which are obvious intermolecular forces. Right, so that covers our section 1 on chemical bonding. In this second paper, okay, we can look at that other paper another day, but maybe let's commit to it, right? Let's commit to it to do it next week and see if we can finish all these, right? Let's see if we can finish all these within, this is the month of what? Of March, isn't it? Yes. So let's finish these within the month of March so that in the next month we are looking at the second topic. And the second topic that we said we are now trying to attempt is ideal gases. The first two, molecular structure and intermolecular forces, in our discussion, we have a lot of, in fact, in our questions, we have a lot of mixing of those concepts. They are interrelated already. So you find that we saw some questions which had to do with the definition of an atom which pulls all the bonding electrons and its tendency to do that. What is the definition of its tendency to do that? We also saw that. And then bond polarity, we see it within. So we saw, for example, we saw difference in electronegativities leading to a certain polarity of bonding, right? So we saw that bond polarity. Bond energy, we can see it in other calculations. Bond length, we had a question on that. But at the same time, within the same paper, we then had a question on types of intermolecular forces. Right, we saw the types of intermolecular forces as these dipole, induced dipole forces, ion-induced dipole forces. So those are the examples that we right. So I think we've covered much of what we needed to do in this topic today. Let's make sure that next week we come prepared. Remember, the paper we will work on next week. The paper we will work on next week is the 2017 paper, right? So we'll work on the 2017 paper. In the 2017 paper, just remember to focus on the questions that have to do with the chemical bonds. Then we do that, and then we know that by the end of March we've cleared and put those away, and then we can move to the. How's that? I hope that will be helpful to you. So this is the end of our discussion. Thank you very much. I hope this was useful or helpful for you. I have to call it a day. Please enjoy your weekend. Keep safe and keep well. It's a goodbye for now.